Oh, look, that one didn't make the weird shape. Huh. Okay, I have no idea what the difference is. I'll take it though. Okay, so chapter 13, we're talking about solutions. Okay, and first part of this is thinking about how a solution can form. So we have a couple of terms that we need to understand. The first one is solute. Purple. And then the next one is solvent. Okay. So a solute is going to typically be the substance that is in smaller quantity. And we talk about dissolving a solute into a solvent. Often we're talking about our solvent will be as water, but it doesn't have to be. In this course, we're typically going to see a solvent that is a liquid. You can actually make a solid solution where you combine a small amount of one solid into a larger amount of another solid and mix them together. But we're not going to focus on that for this course. So that dichloromethane that we looked at on the couple slides ago, that is a liquid. It's a great solvent. And so you could imagine dissolving certain things in dichloromethane. Okay. So again, solute, smaller quantity, that can be both a solid or a liquid. Sometimes it'll be a salt, sometimes it'll be some sort of molecule. We often talk about sugar. So the way we make a solution, there's actually 3 steps. You will see when in practice you do one, right? You put. But what's happening in the solution is essentially 3 different things. The first thing that has to happen is that the solvent has to separate and make it into the solute. So again, when we're thinking about it, remember like the imagine we're water, right? And water has dispersion force, and it's a nice network of intermolecular interaction. In order to get a solute molecule into that, we have to break apart those molecules. That's step 1. The solute also needs to be broken apart into components. So if we have sugar, sucrose, there are dispersion, dipole, and hydrogen bonding actually for everything. We see it as a solid, looks like small cubic structure. We put it in water. But we have to somehow break apart of those molecules into their individual sucrose. Break apart the solid into individual sucrose. That's breaking those intermolecular forces. If it's a liquid, let's say we take ethanol. Ethanol CH3 CH2OH. Okay. What hydrogen bonding present, right? That's molecular dispersion. It's a liquid. Okay, so if we take some of that, a small drop of ethanol, put it in water, that has to break apart in order to be dispersed into the solid form. So again, second step, breaking up those solute-solute interactions. Then, you recombine. So now we have forces that are interacting with the solute and the solid. And those can also be different, right? Intermolecular forces doesn't mean that it has to be within a certain type of species. So we can have hydrogen bonding from one water molecule to one. And then I wrote here, allow them to interact. And what we're going to see is that there's some amount of energy that's released when solute and solvent combine. So it takes energy to break these apart. So energy is released. So we are going to talk a little bit about enthalpy. Okay, and that's here. So in terms of energetics of dissolution or dissolving something, dissolving a solute in a solvent, we need to use the term enthalpy. And we typically think about enthalpy, or we use the symbol delta H, where delta stands for change. Okay, so we're going to assign a number to a delta H. Okay, but what that delta H is really is the initial, or excuse me, the final enthalpy number minus the initial enthalpy number. Okay, we don't need to know what those two numbers are. We need to know what the difference is. We need to know what that change is. Okay. So again, as I said, we have to break apart our solute. We have to break apart our solvent. Those both take some amount of energy. So we have to put energy into it. And when we combine them, we release some energy, okay, and form a solution. Now, the way this equation is written, everything's a positive, or everything is added together, but some of these delta H values could be negative, okay? So if we have our delta H of solvent plus our solute plus forming the mixture, this last step, delta H mixture is forming that solution, then that's the total delta H of solution. If we have a positive value for our enthalpy of solution, that means that energy is absorbed, and that solution, if you were to touch it, if you were to be here and touch it, it would feel cold. Okay, so the way this is always think about it. All right, so we have a positive delta H comes in, but it feels cold. That's how I remember that. We have a negative delta H energy that is really feels hot. Goes up. Okay, so what is happening? What is happening? What is happening at the particle level? We've got some ugly things here. All right, so we're going to put some arrows here where these boxes are. All right, so let's think about two different types of solutions. We're going to think about a salt solution. We're going to think about a sugar solution. Okay, where salt in this case is actually sodium chloride. So when we put solid sodium chloride into solution, it forms the sodium ion and the chloride ion. You'll remember those rules for like ions and what ions form and how they dissolve and all that. Yeah. Now's a good time to go back and think about and look at, remind yourself like what ions are possible. So for instance, this is a good one. Sodium nitrate, NaNO3. If we take that, I want you to be able to recognize very quickly that we could form the sodium ion and the nitrate ion. Okay, so be able to recognize those ions. It's just an example. There's lots of them. The other thing to note is that we have S for solid, AQ for aqueous. So that signifies that we're dissolving this in water. Okay. Same with our sugar, solid, dissolve it in water, now it's aqueous. Notice that the formula doesn't change. with our sugar, okay? So for every sugar molecule that we put in there and dissolve, we have a sugar molecule, okay? It doesn't change. Nothing breaks apart. Sometimes that's really tricky to figure out something that's an ionic species, where you're going to get the formation of ions in water, versus a molecular species where the structure stays the same, okay? So think about that too when you're looking at these problems, how to start recognizing the patterns of what's an ionic species, what's a molecular species. Okay, so in these boxes, we're going to write the types of intermolecular attractions that are present. So for sodium chloride, what type of solute-solute interactions are present? Go ahead and talk quickly to your neighbor. Think about, let's just focus on sodium chloride. Solute-solute interactions, solvent-solvent interactions, and then what solute-solvent interactions are going to take place. Go ahead and take a couple minutes to do that. All right. This is misleading. What types of forces are present in the solute-solute interactions for sodium chloride? Yeah. We have ionic interactions, yes. So we have ionic bonds that are formed. Now, these are not intermolecular forces. Okay, so I apologize. But those are the forces that we have to overcome, these ionic bonds. Okay. So what about our solvent-solvent interactions? We have water. Yeah, all of the things. Hydrogen bonds, dispersion, and dipole-dipole. I'm going to do D-D for that. Okay. Now we're going to take our ions, we put them in their solvent. What are the solute-solvent interactions? What's that? Yes, ion dipole interactions. Yes. Cool. Does that make sense? Questions on that? Yes. Which one? All of them. Okay, fair. Yeah. Okay, so when we have our sodium chloride, that's an ionic compound. So we can tell that by the way it breaks up in water. If that could be a clue, if you need that. So it forms ions. And so the interactions that we have to overcome, or the solution has to overcome to form that, is breaking up the ionic compound into its ions. So there's ion bonds that need to be broken. When it comes to the solvent, these are now not breaking any hydrogen and oxygen within the water molecule. All those covalent bonds, the hydrogen bonded to oxygen, bonded to hydrogen, those stay in put. We're only breaking hydrogen bonds with intermolecularly, so between the molecules. We're breaking dipole forces and any of the dispersion forces that may be present. Okay. So because water has all of those forces, those are the ones we have to break. Okay. And then when it comes to what we form when the solution is formed, because sodium and chloride break apart into ions, the way that those ions are going to interact is by ion dipole force. There's nothing else within the sodium ion or I guess there's some dispersion forces, but the main one is going to be the ion dipole. Does that help? When we look at the sugar molecule, the solvent-solvent interactions or intermolecular forces are going to be the same. So again, we're going to have hydrogen bonding. We're going to have dispersion. And we're going to have dipole-dipole. Okay. In terms of the solute-solute, again, we're not going to break any covalent bonds when we form this solution. So this sugar molecule, which is drawn here, is going to stay looking like that, essentially, in solution. But those sugar molecules, when they're in a solid, they are interacting with each other through those intermolecular forces. And we have oxygen and hydrogen bonded together, right? So there's some OH groups here, a whole bunch of them, actually. And so what forces would be present because of those? Hydrogen bonding, and of course, dipole-dipole, and dispersion. Does that make sense? Okay. Now we're going to take our sugar, and we're going to put it in water. So all these water molecules are going to surround that sugar, and we can have interactions between the solute and the solvent. What can we have? What kind of intermolecular forces? Here, I'll give you one. Dispersion. You're welcome. What else? Can we have dipole-dipole? We can, yes. Water has dipoles. The sugar is going to have dipoles. Can we have hydrogen bonding? Yes. Now, if we take a look at the types of forces present in terms of breaking intermolecular forces and then remaking them, we think about like the differences in terms of their strength. When we talked about dispersion is less than dipole is less than hydrogen bonding. You can see that when we end up thinking about the overall enthalpy of formation of a solution, the magnitude of those forces is going to change delta H. So if it takes more energy to break apart the intermolecular forces in a solute, but it can't interact as well with the solvent, that delta H is going to be different than if we could take a lot of energy to break apart the solute, but it can interact really well with the solvent. Okay, so we're going to talk a little bit more detail about what that looks like next time. All right. Any questions? I guess we have 1 minute. Do you want your minute or was it? Come on, y'all. Feel free. Yeah. Sorry about messing that up.
It's okay. Just like the syllabus doesn't have anything specific.
No, you're right.
I guess this is more.
Click on the module for me. And the homework, like this, the reading of the textbook, you're not going to be graded on.
Yeah, I know that.
Okay.
I just like to be on.
Fair. Totally fair. So I'm going to do most of my stuff here in the modules.
But is this actually what you want on Monday, or did you have to change it because of?
Well, we've only gone like 2-3 slides out of 16 for this section for Monday, 13, 1 and 2. So I think we're probably going to still be there. So that's pretty close.
Okay, wait.
Yeah.
So did you just mess up like today? Like, is all this other stuff accurate? I feel like this is.
I actually need to go through and check it because